This is CX1104, chapter 8.1.2. We'll discuss about characteristic equation. Basically, we want to use the characteristic equation to find the eigenvalues and hence then find the eigenvectors. So basically, we are trying to find a procedure to find eigenvalues and then eigenvectors of a square matrix A. In the last lecture, you realize that somehow we have given you either the eigenvalues and then find the eigenvectors, or given the eigenvectors and then find the eigenvalues. You realize that actually there are two unknowns in this problem, eigenvalues and eigenvectors. So how do you find these two unknowns together? Right, so we began with this problem as usual. First, the definition of eigenvalues and eigenvectors. A times the eigenvector equals to the eigenvalue lambda times the eigenvector. Once we have this, we can shift this right hand side to the left hand side to achieve this equation, reducing it to this form as we have seen in the last lecture, and then realizing that to solve for this equation, this matrix here, A minus lambda I, this matrix must be singular. It must be singular, or in other words, not invertible, because it must have columns that are dependent. When the columns are dependent, then we can find x, a vector x, such that A minus lambda I multiplied by x will be equals to 0 for non-zero x. Okay, that's the procedure. Now we could have gone the other way around. We could have like move this guy to the right hand side, so it will be 0 equals to lambda x minus ax, and then we can then do lambda times I x minus ax, and then lambda I minus a times x equals to 0, which is the last equation. And we also can solve for this matrix or find the correct lambda to make this matrix singular. Okay, so both ways are fine. It doesn't matter which way. Right. So it looks like the key idea is that this matrix A minus lambda I, or lambda I minus A, must be singular or not invertible. So let's go and see the invertible matrix theorem and see how we can exploit this fact. Now be very careful here. A minus lambda I is the matrix to be considered, and here the word A is any square matrix, so we are actually thinking that this is that little a we're talking about. Okay, so don't become confused. So this matrix, this whole matrix here, is A in this discussion. Alright, this matrix is square because A was square, lambda times I, and I is an n by n matrix, is still square, so A minus lambda I is still a square n by n matrix. And the invertible matrix theorem says this: if we claim that A is invertible, then all this is also true, equivalent statements. So if we say that A is invertible, then A is row equivalent, it has n pivots, Ax equals to 0 only has the trivial solution, columns of A forms linearly independent set, and so on. Alright, so what about if we say that A is not invertible? Then when we say A is not invertible, then what we are saying is that we're going to say a lot of this statement, the negation of this statement. We say that, maybe this is more clear, A does not have n pivots. The columns of A forms not a linearly independent set, and so on and so forth. So it's a negation of all these statements. We're interested in this matrix being not invertible. Okay, because remember in the past we want this matrix A minus lambda I minus A to be not invertible. Okay, now among the properties that are most interesting is number E. The columns of A forms a linearly independent set for invertible matrix, or in other words, for not invertible matrix, the columns of A must not form a linearly independent set. Additionally, there's a theorem which we have not introduced yet. We'll introduce it now. For a matrix to be invertible, another of the property is this: the determinant of the matrix must not be equals to 0. Implying if a matrix is not invertible, then the determinant of A must be equals to 0. That's the negation. Okay. Now we're going to use this property explicitly, clearly, to help us solve the eigenvalue problem in A minus lambda I. As I've pointed out, as we have seen, to solve for this A minus lambda I times x equals to 0 require us to know lambda and x. There's two unknowns, and we have to find one unknown, then we can solve the unknown. But since we have two unknowns, we cannot solve for it. However, if we have used this clever idea of determinant of A equals to 0, what we then do is to allow us to reduce the problem to one of only eigenvalue. Let us see how this clever idea works in practice. Alright, first let's review the determinant of a 2 by 2 matrix first. A matrix A consisting of 4 elements A, B, C, D has the determinant as A times D minus B times C. So this is what we know. Now, when the determinant is 0, then 1 over 0 is infinity, so the inverse does not exist. Okay. So the determinant of a 2 by 2 is AD minus BC. Now, remember we want to reduce determinant of A minus lambda I to be equals to 0. So let's start with A first. We have A here, and then we are going to find we're going to write our usual equation to solve. A minus lambda I times x equals to 0, and we want to say that it must have a non-trivial solution. X must be not 0, therefore A minus lambda I is singular, and when we say singular means it's not invertible. Therefore, now let us solve for A minus lambda I. So this is A here, and lambda I is nothing but the diagonal elements of this matrix being lambda, and we can now have 2 minus lambda is 2 minus lambda here, 3 remains as 3, 3 remains as 3, minus 6 minus lambda is that element. We apply this equation. The determinant of a 2 by 2 matrix is 2 minus lambda multiplied by minus 6 minus lambda minus 3 by 3. And this is equals to the determinant of A minus lambda I. Now you open it up. Let's see. When we open it up, we'll get this equation here. So you can work out the math. You collect all the polynomials together, you'll get this equation. This is a polynomial. It has a special name. It's called the characteristic polynomial. And it should be equals to 0, because that's what we are claiming. We're claiming that this matrix is not invertible, therefore its determinant must be equals to 0. Now, we have a polynomial of second degree, second order, equals to 0. We can solve for it, and we found that we factorize it. Lambda can be equals to 3, or lambda can be equals to minus 7, showing us that these are the two eigenvalues of A. Okay, there are some names that you must remember. This is called the characteristic polynomial. It is on the variable lambda, the eigenvalues to the power of n, where n is the dimension of the n by n. In this case, is 2. And now you also see that the number of eigenvalues will be equals to the number of roots, and since it's a second order, there will be 2 roots. Okay. This equation also have a name. It's called the characteristic equation. It's the determinant of A minus lambda I. Alright, with that, this is the first step. We show how we use the characteristic equation to solve for the eigenvalue.